Einen schönen guten Morgen. Good morning, everyone. First talk in Hörsaal 1 at the 20th FrOSCon conference. Woo! It's lovely to see so many people already here this early for a hacker. Our speaker is going to talk about file systems, and I mean file systems. I mean, what do you want to talk about an hour about file systems? It's a solved problem, right? Well, well, actually, without trying to spoil anything, please welcome for 50 years in file systems, Kristian Köhntopp.
Hi, I'm Chris. I'm old. I got my first computer in '83, and I think I went online in '87 or '88, I don't remember. And I think the year after I got my first Unix system. And since then, I haven't been offline much. I have written a series of blog articles about file systems. So instead of the slides for this talk, you can also go to the blog Köhntopp info, and click on the file systems tag and then read the long version of that. I started that blog series mostly because if you look back, or if you live in current times, you often ask, what is innovation? What has changed in the things that I work with? And I sometimes stop and then try to understand what happened in the last few years in my profession to better understand what the general direction is in which we move. And one thing that is important for me and my work are file systems, because I work with databases a lot, and that means that I'm somewhat interested in how the data is stored and how I can get it back and how everything performs. Databases and file systems are a thing that is not very amenable to the usual web developer YOLO stuff. I go and deploy something, and then if it doesn't work, I roll it back, because that is where the state of all those stateless systems is kept. So you roll back to the old version, but well, the data is still gone. So correctness is important, and that also means that progress is slow. That means we see progress in the area of file systems in like decades. You see 1974, 84, 94, 2004, 2014, and then you can see or observe how things change and what is new. It is also an interesting scalability problem, because most files are tiny, and you have very, very many of them, often very many in a single directory, and that initially performed like shit. And then you have a few files that are very large, and they also need to perform very well. Most files are written front to back, and then they never change. And some files, especially the large ones, are changed very often, and then with a lot of seeks and in the middle. So you have both use cases, immutable things and mutable things, and both need to be handled as well. And you have long-term problems. Most files actually live longer than the programs that created them, which means that you have to do version upgrades. Most file systems also live longer than actually the computers they are initially created on, which also means that you have, at the file system level, compatibility problems, back compatibility, upgrades, and all these things, and often in place. The blog file system series that I wrote was about the evolution of Unix file systems. So there's a lot of things that I will not cover. I could cover them, but then it will be evening and we need to continue tomorrow. And that means that your favorite file system will not be covered here, unless it's one of those on the left-hand side in green here. Operating systems are in general there to abstract away and virtualize things, to manage them and provide some kind of abstraction that you interact with. So for CPUs, you get the scheduler and many processes that share one CPU or the set of CPUs that we have. But usually you have far more processes than you have CPUs in the system. The network, you have one cable, but there are very many packets and very many connections, often multiple connections per program that is running. Memory works the same. You see your linear address space, but in reality, the memory your process uses is scattered across the whole physical address space of the system. And this worked that way as well. At least they started to work that way about 1970. Before that, you have maybe physical disks that you use directly, and it is a problem left for the exercise of the programmer to do something with disk blocks. Or you have virtual disks in some kind of mainframe that you can treat like this. Or you have the opposite. You have elaborate file systems that think they are databases and provide record structures and the ability to insert records in the middle of a file and things like that. And in 1974, approximately, we get the first Unix file systems. The first really popular Unix system that you can find is the PDP 11 version 7 Unix then. And the PDP 11 looks like this. You have a 16-bit machine with no clock, no memory, and no disk. That means you run at 1 megahertz. You have a few kilobytes of memory. Your CPU is no longer a mainframe, a whole box, but it is several boards inside the machine, but the memory and the disk and everything else is either in the same chassis or in the same rack. And you have a few megabytes of disk space that you can work with. How tiny is that? If you look at the configuration subsystem, conf.h, a file that you change before you recompile the kernel, you see several constants. You see, for example, the system can have at most 150 processes. We have 29 buffer pool, file system buffer cache pages. You can have 20 files open. You can mount 8 file systems. And all of these things are actually static arrays in C that are sized with a constant. And if you want this differently, you have to recompile the kernel with the new configuration parameters and then reboot. And then you have a differently configured system. The disk is a sequence of blocks, starting at the beginning with block number 0, and then it is n blocks long. And at the beginning of the disk, you have a super block, and then a few blocks that maintain information about free blocks on the file system as a list of all things. You have an inode free list, and what an inode is, we will cover very, very shortly. And then you have a bunch of reserved blocks, again, a fixed array of blocks that are the inodes. And you have a few things that have been set in stone at that point, and they have not really changed since then. We know that everything is a file, and everything in Unix even today is a file, except a few things that have been implemented differently, and they usually went badly, like all the System 5 IPC, for example, that is utter garbage. Again, System 5 FCNTL logs that allow you to do range logs, but that work in a very weird way. And so whenever we did something in Unix that did not treat something as a file, usually that was a garbage interface. A file is a sequence of bytes. There is no structure, no record structure in any way that is imposed, and that is left as an exercise to the application developer. If you need structure in a file, use a database. The operations that we have is you can append to the file, or you can seek really quickly inside the file, change your position, and you can overwrite parts of the file. There's no insert operation, only an append operation. And the seek is instant, which sounds like something that sounds very normal. But if you, for example, on an MS-DOS FAT file system where the file is a linear list of blocks, then a seek costs you actually a lot. So there are ways to build a file structure that is really slow when you want to change the position inside the file. You have to work for that, but it is possible. And one of the core concepts of the Unix file system in 1974 already is that we have like 2 different subsystems. the lower file system that implements a nameless sequence of bytes, the file, and that is controlled by the inode, which stores basically the block list and a few items of metadata, but not the name. And then you have the file system tree with the naming and the directories on top. And that is being implemented pretty independently from the rest. That also sounds normal to most people who grew up on Unix. But again, it is possible to build that differently. Again, we can look at the various Windows file systems that do that differently. And it turns out it is a very bad idea to make it differently. This way, we will later see, we get a lot of flexibility and a lot of, it's a very durable concept. This has not changed at all, and it has been actually enabled a few other innovations. You can also see that this layout here is not really smart, because in order to find a file, you have to go to the root inode, that is typically number 2, go to the directory block that contains the directory. Directory is a list of names and inode numbers. Then you have to go to, say you want something here like user. You have to go to the other inode, back to the beginning of the disk, find the blocks, go to the list, and when you have found this, you go to the next inode and so on. So you go back and forth all of the time. And if you're in the unfortunate situation that you have a mechanical disk, it means that the disk head has to go like this all of the time, and that is anything but fast. The inode itself in 1974 looked more or less like this. And if you look at the drawing of the entire thing, this is from the book from Maurice J. Bach about the 1974 Unix source code. You see that you get this. This is basically a compressed array. Like I said, we have very many tiny files. So tiny files should be stored in a very compact way, but we also need to accommodate large files. So what we have here is an array, and that array would be the array of 40 bytes, the DI address thingy, that contains block numbers that make up the file, but it has only space for a few blocks. And after that, we have the location of an indirect block, and the indirect block points to a full block of block numbers that make up longer files. And if you have even longer files, you get the double indirect block that points to a number of blocks that point to indirect blocks that then point to actual data blocks, and so on. And usually that goes no deeper than 2 or 3 levels, in the beginning 3 levels. And when we make larger blocks, we can make do even for very large files with 2 levels of indirection. This is very slow to access blocks in very large files, unless you have a file system buffer cache, because basically you need to cache all of these blocks for this to be fast. But if you have a system that has very large files, you probably also have the money to have enough memory to have a large file system buffer cache, and then that works quite well. Also, large files are rare, because they occupy a lot of space on the disk, so you can't have many of them. Your file system can be broken, it can be inconsistent, and then you have to do a lot of things in order to reconstruct that. Basically, at this point, you have to read the entire disk. And then you have to prove that a number of assertions are true. Like, for example, you read the superblock, you read all the inodes, and all the blocks they point to, and then you should know about all the blocks that are used in your system. That means you can construct the free block list by subtracting all blocks from all blocks, the used blocks, and those that are left is your free block list. You have read all the inodes. That means you can reconstruct the entire inode list, and you know then also which inodes are free. You have read all the directories. That means you can check that all block numbers appear exactly once. There is no block that is used by 2 different files. That would be bad. And you can also make sure that all inodes have at least one name. And if they don't, you give them a name that is the inode number and put them into the lost and found directory. And you can also make sure that all directories have the same structure. That means they have a dot and dot dot entry as the first 2 entries, and they actually point to the correct directories. All of that is incredibly slow. And it's proportionally slower the larger your file systems are and the fuller they are. And it also uses an insane amount of memory, because you need to keep all of these lists in memory. You can write them nowhere because you have no file system yet. If you boot the system with an incorrect or inconsistent file system, you have to actually do all of these things in memory before you can write them out, and you have at least the root file system for temporary storage to work on other things. You have very many tables in memory. You have no swap on boot. And if you do that on a PDP-11 in 1974, you will find that you probably do not have enough memory to keep all of these things in memory. So you need a tiny root file system, and you need to put everything else on another disk, so that you have at least the root file system to continue to work for the other disks. And that is why you have USR. That doesn't mean user, it means Unix system resource. And it contained user directories, but also user bin and other things. And on the root disk, you have only the tools that are necessary to boot up the system. So you have an initial file system with free space, so that you can complete the boot. On today's system, that is utterly unnecessary, because we put entire DVDs into memory multiple times, like 10 or so. And that means even if we still had file system checks like this, we could simply do that in memory, write out the correct file system, and then continue to boot. Or we boot the entire system in memory, check all the disks, upgrade them, write everything back, and then reboot into a sane system. So if your system still has a user and has not abandoned that, maybe the distro should be modernizing, because you don't need any of that. How many permission bits does a file have? Yeah, but how many does it have? Huh? Too many. How many permission bits does a file have? More than 4? It is 12. Because you have read, write, and executes for the user, for the group, and for others. But you also have SST. You don't see them, because they are not set, except when they are set. They are shown here. What does a large T mean? No, what does a large T mean as opposed to a small t? Yeah, it means that the X behind the T is not present. So if you see an uppercase T, it means there is no X behind it. If you see a lowercase t, then it means there is an X behind that. The same for the S that you can see here and here. What do they mean? We don't know. It is very much dependent on if it's a file or a directory. It is also very much dependent on the operating system versions, especially for the T bit. The T bit on a directory changes the behavior of the delete. The T bit on a executable changes the behavior of the kernel for the binary, if it's a PDP. It does not do much on modern system, and the T bit on a non-executable file does nothing. So it is no wonder that you don't see them very often, because they are not used very often. The S bits you used to see a lot for set user ID and set group ID binaries. So to get binaries with privileges that you could then exploit and become root yourself on the system, Caliph instead of the Caliph. But there are other more modern systems today that do that better. So we see them less and less these days. What permissions do you need to execute this command? Yes? Well, you need a lot more permissions than you think. You need execute on root, you need execute on etc, you need read on passwd, you need execute on root, execute on bin, and execute on cut. You have a very weird shell, but yes, okay. Then you don't need that. Found the set shell user probably, because normally it's not built in. So there is a lot of permission checking going on a system, because we have to traverse paths all of the time. And every time we traverse a path, we need X bit on the directory, to be able to traverse that directory to get there. So if you see /etc/passwd, you need permissions on the root directory, you need permissions on the etc directory, and then you need the actual permission on the file to do whatever you need to do. And the same is for binaries, and there you don't even see the path because the path is a shell variable and you don't have to type it every time. But if you /bin/cat /etc/passwd, then you can actually see all of these directory traversals as well and all the X bits that you need. That is a nice test if you have German Azubis. You go into a virtual machine, you take away the X permission on the root directory, and then you ask them what is wrong and how do you fix that. That is how they learn about permissions, and that they're much more complicated than they think they are. Yes. Another thing that most people are not aware of, many developers aren't, is that writes are atomic. That means that a single write system call, even if it's a complicated write system call, like a more modern write PV, scatter gather IO for the V and P with positioning, so that the writes are one system call with many writes and many permissions, taking an array as an argument. That is always atomic. So if you have like a 10 megabyte write and a second 10 megabyte write, that is surely more than a single block. And if they two overlap, you will not get this write and this write intermixed, even if they are supposedly running concurrently, because this is locked. And that means that one write is completely before the other. And it's either this situation or this situation, but it's never block solid. So writing a single write system call actually matters because it gives you guarantees. It also costs you performance. Why does it cost you performance? Because it's implemented still to this day in the 1974 way of doing things, except in one file system. And that is here, you have the write system call, and on a PDP in 1974 that calls the RDVR procedure. That then first takes the P lock, then does the actual thing, and then does a P release. And the P lock function is a thing that is actually for atomic writes and pipes, but is also used for all other writes, because it happened to be there. So it's not a P lock, it's actually an I lock. And that takes a lock on the I node, and then you are alone on that file, on the entire file. So imagine you're a database, you have 10 or 20 writer processes on a single file. How will that perform? So Ingress tells you, or told you back then, use a raw device, because if there are no files, there can't be logs. Oracle tells you, use table spaces, because if you have a table space that is made up of many files, each a gigabyte in size or something, then you have a lock on every file, but you don't see that because it's a table space in the database. And that's better because you can use file system tools to back up the whole thing, whereas in Ingress you're basically alone and you have to use the database tools. And other databases tell you use XFS because with ODirect they don't have these locks anymore, and that's the only file system I'm aware of that does it that way, so the problem doesn't exist. That's actually the proper solution, but yeah. Directories in 1974 are 16-byte records with 2 bytes inode number and 14 bytes for the name. And if the file name is not 14 bytes, then the rest is filled up with zeros. So any byte, including spaces, quotation marks, or control characters like return, can be part of a file name. It's totally valid, except for the 0 byte, because that's the padding character, and the slash, because that's the path separator. That is also not true in 2024 anymore, because many file systems require that you form a valid UTF-8 file name. But there are still file systems like the various extended file systems, 1, 2, 3, 4, that allow you to basically put binary garbage in file names, and then you have to deal with that. There's the B option to the ls command that will show you then nice octal, instead of terminal garbage for such file names. So where are we now at the end of 74? We have a file system that actually works. It is extremely dense in tiny code. If you look into the Unix history repo, there's the source. You probably won't understand what they show you, but you can read this. This will explain what you see here if you go to the V7 branch for the PDP and navigate the source tree. It's about 500 lines of code. It's really, really dense. And it gives you the idea of one seeks, fast seeks, blocks and byte arrays as files, atomic writes, two independent systems, inode array versus the directory hierarchy. The name E function that traverses the path name and converts it internally to the inode number. There's no way to pass an inode number to the kernel. You have to go through the name E path traversal to get one, but the kernel only works on inodes. And it also does the permission checks. That way the permission checks are integral part of the entire thing. You have 2 byte inode numbers. You have 65,000 files per file system per mount. That's not adequate today, but it was back then. You have 16 mega blocks in a triple indirect file. That is not enough. At 512 bytes per block, that gives you 8 GB files or something, if I'm not mistaken. You have 1 writer per file at a time. Your directory lookups are linear list traversals. They are slow as fuck. You have no mandatory file logs. That is arguably not bad, because if 2 programs concurrently work on a file and don't know of each other, this is a very bad situation anyway. And if you look at Windows systems, for example, they have mandatory file logs, and that means that every backup and every software update has to have a system reboot, because there are few files that are always locked, as long as the system is booted, so that you can't make a backup without a reboot, and you can't make an upgrade without a reboot. So maybe that is not as good an idea as it sounds when you talk about mandatory file logs. There's no delete system call. There's unlink that removes one name of a file. A file can have multiple names because the inode system and the naming system are independent. And the file is deleted when it has no names and when it has no users, when it is not open. Anybody who has ever deleted a file in varlog and then wondered where the disk space is, why it doesn't come back, knows that by heart. It's an experience that every sysadmin has to go through. And initially, there's also no makedir, no mdir call. That will turn out to be a very bad idea. And there's also no rename system calls. You have to link and unlink 2 system calls in order to simulate that. That is also a very bad idea. You make a make not that makes a device node of type D directory, and then you make 2 link system calls for the dot and dot dot entries. So that are 3 system calls to make a directory. And that is not atomic. That means there is a race condition. And that means somebody can make a directory where the dot dot entry does not point to the parent directory. And the next time the file system checker comes around, it will delete your file system. Or at least that subtree, because it's completely invalid. You can also technically make a hard link on a directory node. That means you have a directory with 2 names. That means your file system tree is no longer a graph, a loop-free graph. And that means also that your file system checker will run amok, because it can be a circular graph, and then it will never finish. So having a makedir system call is really, really, really important. We don't have that here, not yet. And you also have no bitmaps. You have free lists for blocks and inodes. They basically work as a last in, first out. That is a block mixer. So you have a mechanism here that maximizes file system fragmentation, because the blocks that have been most recently freed are the first one to be reused. And that means you have a giant block shovel. You have giant amounts of free space that are never used, because you always reuse the most recently freed blocks. Yeah, and you have a file system checker, and that's annoying. We jumped 10 years. That photo is in Frankfurt. There used to be in the performance test center in Langen, where Sun used to have a museum as well. And right at the entry, you see that poster. The student had to build his workstation himself 10 years ago. And you don't have to, you can simply buy one now. You have a 32-bit CPU often a 68,000 variant from Motorola. You are in the age of the rise of the RISC architectures. You have MIPS in SGI systems. Sun goes from the 68,000 based Sun 3 systems to the Sun 4 systems based on the Sparks processors. PA RISC from HP comes and dies very quickly, and the DEC Alpha comes very quickly and also dies very quickly again. You have 2-digit numbers of megabytes of memory. You have 2-digit megahertz clocks rising very quickly to 3-digit megahertz numbers. And you have a paper that appears in 1984, a fast file system for Unix, and that's the BSD fast filing system, BSD FFS. It deals with the fragmentation problem. Fragmentation is a non-contiguous sequence of blocks in a file, and fragmentation is actually not a problem, even if MS-DOS users believe differently and religiously defragment their hard disks in 1984 and even in 94 and even in 2004. A problem is only a short sequence of non-contiguous blocks, one that is shorter than the read ahead of your file system, whatever you need in order to process while the disk performs the disk seek. As long as you need longer to think about the data you just read, then the disk takes to seek, you're fine. So there is some arbitrary hardware-specific number of blocks that is okay to have as a sequence, and anything shorter probably is not so good. Yeah, fragmentation is when you delete the blocks B1, B2, they are free, and then you write a new sequence of blocks like this is longer, and you reuse these two blocks, but the third one is then here, and that's the bad thing. So the innovation, one of the innovation is we get cylinder groups. If you look at the physical arrangement of blocks on a hard disk, you have several hard disk platters that form the rotating RUSC that is a hard disk. And then you take a few of these cylinders and make them into one cylinder group. Then you take the next inner ring of a few cylinders and make them the next cylinder group and so on. And each cylinder group is its own mini file system with a super block with now bitmaps instead of free lists for faster and more easier contiguous allocation, and with its own set of inodes. And you can now try to arrange files so that files are close to their inodes in the same cylinder group, and that everything else is spread out in the same way. That way you get long-term stability of the file system. You do get some fragmentation. Actually, you even introduce some fragmentation on purpose in a controlled way, but so that the fragments are large enough. And that way you get a file system that even over long-term use does not turn into a block mixer and gives you sane performance and also like equal use across the entire hard disk. This requires a lot of knowledge about the actual physical layout of the hard disk. And in 1984, we had the singular point in time where a system can actually have knowledge about the physical layout of blocks in the hard disk. Very soon we get the controllers integrated with the hard disk, and the controller will lie to you about the physical layout of the disk. And then you turn from CHS addresses, cylinder, head, and sector, to linear block addresses. So you're back to these block arrays from 0 to n. And then you get fake CHS addresses about hardware arrangement that is not actually there, with 63 platters that are really 1 or 2. And other lies that the controller has to give to the system, because the system falsely believes it has a right to know the geometry of the drive. When the system is not even able to handle the geometry of the drive, because it becomes a lot more complicated as well. Like you have more sectors on the outer cylinders than you have the inner cylinders of a hard disk, because the paths are simply longer, so more sectors fit. And very few operating systems are actually equipped to handle that in any way. You get larger blocks, but most files are tiny. So if you run a file system with 4K or 8K blocks, a lot of waste exists. Giving file system populations back at that time, we don't have multimedia yet, so most files are text files or C-source files or similar. With 4 and 8K blocks, you have loss of unused tails of large blocks that make up the majority of the space used, like more than 50%. So we introduce sub-blocks or fragments to fight internal fragmentation. You put the ends of multiple files into a single block. You have an 8K block that has 8 fragments of a kilobyte, for example, and then you have the ends of 2 files, the final 3 kilobyte of one file and the final 1 kilobyte of another file in the same 8K block. Of course, if that file ever grows, that is very slow. You also introduce the idea of pre-allocation. As long as the file is open, it only grows in 8K blocks. And when we close, we find space for the remaining few bytes as fragments somewhere else. And that means that, for example, your log files, which are always open, will always grow in 8K full blocks. And only the files you save from your Emacs will actually end up as fragments because they are tiny. And then share that with another file. We introduce long seeks. We look at the cylinder groups. And if we write a very large file, then we, on purpose, change the cylinder groups so that the back blocks of a very large file go into a different cylinder group. And back then, that meant that every megabyte or so, we do a long seek and go to another cylinder group. You have to think of these cylinder groups as mini file systems, each of them, and you want all of these to have a few free blocks because they have free inodes. So if you create an inode and a single large file occupies all the free blocks, you can't put the first blocks of your new file close to the inode because all of the space there is already occupied by a single large database file, for example. And that means that after a megabyte or so, we force the large file to go to a different cylinder group so that free blocks remain here. And when we create another small file, the few blocks that the small file occupies can actually be placed close to the inode and so on. This is a very simple logic. It has to be because we cannot allocate files as units. We can only allocate them by block. The file system buffer cache must make sure that we only ever have a single copy of a block in memory. Because otherwise we get a cache update problem. We update this copy, but not that copy. We also waste memory. And we index the file system buffer cache with the device number and the physical block number. And that means the moment we allocate a file system buffer cache block, even if it's not yet written, we have to make a layout decision for a singular block. And it can't know anything about the previous blocks or the blocks that are not yet written that will come later, even if the sync, the flush of the blocks, is not yet there. We have to lay out every block on itself. So how do we implement large seeks, long seeks then? The answer is we simply look at the offset. And then we take megabyte steps. We cut away the lower 20 bits of the offset and take that as a displacement from the initial cylinder group. Then we look at the target cylinder group, check if it has still space, and if yes, we put the blocks there. If it doesn't have space, we just jump further and further, cylinder group by cylinder group, until we find one that suits us. So it's very primitive. It's also very tiny code. It kind of works, experimentally shown at that time, that the population is stable and that we get large fragments, large enough. And if we say here, choose the cylinder group smartly, looking at the block inode ratio, that is also a very simple algorithm. The extended 2 file system tries to do better. It actually maintains a list of block group descriptors that are part of the metadata. So you have the superblock, you have the inode bitmap and the block-free bitmap, and you also have immediately after the superblock and before the bitmaps, you have the block group descriptors, and they contain the, among other things, the number of free blocks and the number of directories and the number of free inodes for every block group. And we can then cache that in memory and make this decision where to place things faster. It also means that if file systems get larger, you get more black groups. That means that this block group descriptor array becomes larger and takes up more space. And initially, like the superblock, because it was considered part of the superblock, the block group descriptors also were copied together with the superblock for every block group. So if you have a very large file system, the block group descriptors actually take up all space. And you can't store anything on the maximum sized extended 2 file system in Linux, unless you also, which is default by now, specify sparse super, which means that you do not have gazillions of copies of that entire stuff, but only a few in strategic locations, which obviously is much smarter. Another thing to force spread out of data across the entire disk in different cylinder groups or extended 2 block groups is making directories. When you make a directory, the directory will be placed in a different cylinder group. And the files in it will be placed close to the directory, so in that new cylinder group. So every time you make a directory in BSD fast filing system, you also force jumping across the disk. And you can test that if you make a directory structure like this here, and then do an ls -i and look at the inode numbers in an extended 2 file system or an actual BSD fast filing system. You can see how the directory numbers, the inode numbers of them, they are completely different than the inode numbers for the files that you make, which are very similar. And because these things are also implicitly determining the position on the disk, you know that they are in different cylinder groups. We finally get long names by getting a smarter structure for directories, but it is still a linear linked list, and that means that long, deeply nested file system structures or large directories are still very, very slow. You can now have 254 bytes per file name, and it's still random garbage bytes. And directories can contain empty space, and they never shrink. So you can have a directory with 3 entries that is like 4 megabytes large, because it never shrinks. You get the make new system call for the reasons we already discussed. You get the rename system call. They are both atomic because they're system calls. And that removes a lot of races from the file system. You use bitmaps. That makes layouts of things a bit easier, but you still have per block layout. And you have quotas as part of the file system because that was used as a university. Obviously, students will use all of the space on all of the disks all of the time, unless you limit that somehow. Quotas allow you to do that. And because of that, the ownership is now privileged, and the group ownership is also privileged. You cannot give your files to somebody else, because then they will go on their quota. So you make a directory that only you can traverse. You make a directory that only you can traverse, and then you give all your files in ownership, publicly writable, to me. So they will be on my quota, but I can't get there because the directory prevents me from doing that. And you can work with them because they're publicly writable. So change ownership call obviously is now privileged. It wasn't before. And we get a group set, a number of groups that you're also a member of, in addition to the primary group. And you can only change group things to groups in your group set. So with group quotas, you can't give all the files in your project to some other random project so that it goes on their quota. That is also prevented. We get the flog system call that can log entire files, and it is bound to the file descriptor, which means that it's automatically collected when your process dies, unless the other system that System 5 invents. And we get symlinks, which means we can now have redirections in the file system that even span mount points. That is a lot of good things that happen here. This is so good that, for example, the extended 2 file system in Linux is pretty much a faithful reimplementation of the entire thing in features, but the code is completely differently. And back then, when I had reason to look, it was not really good. The BSD file system code was much, much tighter. It has since been cleaned up quite a bit, but back then, it was mostly, you could see that it was written quickly, not with prettiness in mind. The cylinder head sector address system cannot be maintained. Also, at some point in time, we will completely get rid of hard disks so that it becomes obsolete anyway. Directory lookup is still very bad. File system check still exists and is expensive. And the internal in-memory log structures that are part of the file system will also not scale under load. What does that mean? We will see in a second. If you want to know more about all this, there's another book, this one. You probably have seen the logo already. That will discuss that in much more depth then. 94, we get proper computers. Yay! MIPS CPUs, hundreds of megahertz, FPUs, GPUs, fused multiply add instructions as early as 94 for fast matrix multiplications, gigabytes of memory, very many CPUs, dozens of SCSI controllers in one single box, and that means hundreds of disks in a single box. And if you try that out, the BSD fast filing system scales like garbage again, because it's not built for that kind of machine. We need to do something. We want scalable, predictable performance, especially for video streaming, for example. That means also we need guaranteed latency. If I send a read call, I have about 25 milliseconds for the data to be in the memory buffer, or there will be flicker, and then somebody will be very angry at us. So we need to build something. BSD has BSD fast filing system hacked. That doesn't work very well. It fails to scale to actually this size of machine. It fails to deliver video streaming. And the FSCK file system check never terminates if you run it on that kind of system. So that doesn't work. We want concurrency. We want scalability. We want predictable performance. We want a logging file system so that the check is proportional to the amount of data in flight at the time of the crash, and not proportional to the amount of data that we have, which would be much, much longer. Logs are the thing now. We split the entire thing into zones. We have no global logs anymore. For example, when we want to allocate a new inode, when we want to allocate a new block, there's no global log on the bitmap anymore, but we have allocation groups that are no longer cylinder groups, they are abstract groups and much, much larger, gigabytes in size. And we then can concurrently allocate blocks from different pools because each pool has its own log. We use B+ trees everywhere instead of linear structures, so we have fast lookups, we index things, we organize things no longer as bitmaps or singular blocks, we organize always things as extents, pairs of a start and a length. And for even large files up to a few gigabytes in size, if there is no fragmentation, the entire file can be described in 8 bytes, 4 start bytes for the start block and then the length of the file in blocks. And that's the entire data in the inode that is necessary to describe that block. And in the free map, we have again that kind of structure that describes also runs of free blocks. And because it's a B tree, we can index that multiple times as well. We can index it by start block, so we can find blocks that are close to us. And we can also index it by length, so that we find runs of free blocks of the right size. And the only thing that we need to do is we need to completely rewrite the file system buffer cache, which should be trivial. The BSD fast, the system 5, the V7 BDP file system was about 500 lines of code. The BSD fast file system or the extended 2 file system are about 5,000 to 8,000 lines of code. And the XFS file system in the kernel is about 50,000 lines of code because of all the indexing and trees and the other things that go on. And for all these things, it's also true that the userland tools are about 10 times the amount of lines of code that you have in the kernel. So for the extended 2 file system, you have 5,000 lines in the kernel and about 50,000 lines in userland. And you can imagine what it looks like here. Yeah, we have allocation groups. I already mentioned that. We get rid of the global logs. You also you want 64-bit or even larger block addresses, but you don't want to spend 8 bytes. So you make all addresses relative to the allocation group. That means you can make do with 32-bit block pointers, even if you have a 64-bit file system. That is rather smart. You have concurrent writes. You don't get block salad for 2 overlapping concurrent writes. But you do that, at least in Linux in direct mode, by storing a B tree of writes that are currently active in the inode or dangling from the inode. And as long as 2 writes do do not overlap, they can actually be executed concurrently. Databases love that. Everything is a B tree, I already said that. And that is not just good at the allocation layer, it is also good at the driver layer, because you get very long runs, full extents of writes. That means you can hand over megabytes of writes, full extents, to your driver layer, and that can just turn on the DMA, let the drive do its thing, and the driver can do another thing in the meantime. You need a bit of back pressure checks here to not overload the driver layer with too many entries in the queue, but that is not that much additional code. And you can index the B trees to your hearthstone content, so you do not have linear lookups anymore. You have always logarithmic lookups here. You get dynamic inodes. So you don't allocate the number of inodes in your file system at the beginning when you make it anymore, but XFS will make inode as you go along, 64 apiece, and it will place the files close to the inodes as well, and it will place directories away from the directory it is in into a different allocation group, so that the file system uses the entire disk. Or actually, most of the time, if you have very many disks, you probably will have a volume manager, so your file system spends very many disks, and that means that the directories are probably away from the directories they are in, and that means they are on a different disk. They can act completely independent, and that is also a good thing. You need to rewrite the entire file system buffer cache, because you can't allocate things anymore by the physical block number, or only that. You can also index them, you need to keep both to be able to eliminate duplicates, by the device, the inode number, and the offset in the file. That way, you can identify a block uniquely, but you don't have to make the decision where to put it in the file system yet. That means you can actually write, say, an entire DVD, several gigabytes of data, and then close the file. Then XFS makes the layouting decision, can write the entire DVD if it has a large enough amount of space that is contiguous, as a single write, and without any long seeks or any seeks at all in between. And that means when you read it back, you can also stream that as a dedicated RAID. And if you put a bandwidth management layer into this as well, you can say, I need this many megabits per second. The driver will allocate that, and then it will DMA at the rate with minimum buffer overhead and guaranteed target times stuff from the disk. And that is, for example, what made SGI so popular around 2000 for video work. You have aggressive pre-allocation, and by default it's on. So if you're using XFS on your var log, your disk will suddenly look very tiny unless you mount the entire thing with alloc size and ask XFS to allocate less aggressively. Does that work? Oh, yes. On that system with 20 SCSI controllers and with a few hundred disks, you actually get about 75% of the raw disk performance from the file system, which is awesome. And you can see that it scales mostly linearly. That means that even on a very large system, it will actually deliver you all the performance. So you can simply throw money at the problem, buy a larger machine, and it will work. This is good. But other people thought we can do better. There is a paper about there's a lot of research at that time about distributed operating systems. Sprite in Berkeley, Amoeba, Tannenbaum in Amsterdam, Plan 9 at the Bell Labs, and so on. And the Sprite people with Oosterhout, they wrote in the paper this. Basically, they say it's Batman, but for logs. Yeah, or Bane in this case. You think the log is your ally, but you merely adopted the log. I was born, designed for it. Which means that other file systems have logs. Our file system is a log. And that means in 92, we get the log structured file system from all the BSD people and Oosterhout. The BSD people take the work from Oosterhout and port it to BSD and improve it. And one of the core tenets is we have plenty of memory. disk reads are always cached. It doesn't matter how things are layouted. Even if the log completely shittily contains all the blocks, it contains all the blocks. Eventually they will be in memory, and that will be fast. So only writes matter. The writes are log appends, so they are always fast. Turns out disks are finite, and memory is even more finite, especially in 94. You need a cleaning woman that goes across your disk and rearranges things. Oop. What do? You do basically the same thing that the Java garbage collection does. You identify old, middle, and young generation. You clean up the young generation pretty aggressively, and things that survive long enough go into the middle pool and then into the old pool, and those segments become larger, and things are good. It does mean that you do not write things just once. You write everything at least twice, or even three times if you have the three generations. You have write amplification, you have a seek budget, and this works pretty well with most files because they're written once and then are immutable and eventually deleted. But especially for databases, it performs like garbage. It performs not at all. That means that the premise we have, this here, that is actually untrue. The log is not permanent storage because we have to rewrite it at least 2 or 3 times. And we find this misconception that the log is permanent storage quite often. We find that in the Redis AOF, in event sourcing, and in very many other things. So what is the win? The win is that we avoid mutability. Blocks are never overwritten. They're instead written multiple times. And what's the price? The price is write amplification. The BSD LFS port works pretty well. I've said that already, but the interesting thing is that here on the right-hand side, we get transactional writes. We write things out, and then we write other things out that describe what we have just written. That is this here. We write all the data. Where is it? No, it's somewhere else. We write out the data blocks, then we write out the indirect blocks, then we write out the double indirect blocks, then we write out the new super block. That means that we write out every single write and then a few other blocks as overhead, but it also means that with the sequence of super blocks, we get like file system snapshots. The cleaner will eventually throw them out, or we keep them, then we have snapshots for free. We just have to tell the cleaner, this snapshot is dear to me, please do not clean that up. We can also add checksums, then we get a Merkle tree, a tree that has checksums on the blocks and then checksum blocks. And that will then later become ZFS. Meanwhile, at Sun, that is a fun paper to read. Larry McVoy takes the BSD FFS code and tunes it so that it uses extents like SGI. And the patch is super tiny, and the paper is ultra short. And it basically, the paper is extent-like performance from a Unix file system. And the patch outperforms LFS consistently and without tuning. So all the database tuning and all the work that McCusick and Marco Seltzer and the others do, the original BSD FFS people do with LFS. Larry McVoy at Sun says, hey, I can do better. Look at my tiny patch. He doesn't say that, it's an academic paper. But he totally does say that, academically, of course. And Seltzer writes a paper, file system logging versus clustering, that's the stuff that, with the extents that Larry McVoy does, a performance comparison. And there she curses academically at Larry McVoy because she has to confirm benchmark by benchmark McVoy's findings and give that to him. And the root cause she identifies are the excessive disk seeks from the cleaner. So please give me a hard disk with no disk seeks. You can have an LFS that performs, but it's not on hard disks. You need SSD. They're not there in 94, but they come slowly. And then we get ZFS that does this, that does what Episode does, another file system that we do not cover, from the DCE Foundation, the DEC Alpha people basically. And that does nothing new. They say that in the ZFS paper. We take all the stuff that the other people do, but we do not take their source. We re-implement that cleanly from scratch, and that is our actual contribution. But they do the LFS stuff, add the checksums, do the containers with multiple trees, snapshot management, and logical volume management from Episode, and put all of that together. How much is a zettabyte? It's 2 to the power of 70. And that's about the entire internet traffic of 2016. So a zettabyte is not that much. Zettabytes are NSA level problems. If you want to store all of the traffic of the internet of a year in 2016, you need a zettabyte of data. If you look at disk error rates, it means that the zettabyte of data, even if you buy the most expensive hard disk SSDs that you can get, you still have 100,000 unrecoverable read errors in your zettabyte, and that's probably unacceptable, so you need redundancy and you need checksums. ZFS gives you that. And then it builds on top of each other the various things that give you a POSIX API. Actually, it gives you POSIX API, but at the lower level, it gives you something that could be object storage. And that means we have, with ZFS, file systems as a solved problem, except for databases. Again, we get object storage. We say, OK, if mutability is the problem, let's get rid of the update. Let's make everything immutable and then leave the problem to the database designers. And instead of CRUD with updates, you get CRRD with atomic replace. And you also get rid of the metadata limitations of POSIX. You now have a complete key value store for metadata that is indexed. And then we don't know how that works, at least not for S3. We do know how that works for other object storages, for Rados, for MinIO, and so on. And where does that leave databases? Well, you now have to make do with slow storages, because they usually do not have longer file system call, operating system call interfaces. They have a REST interface, so very, very high latency. And that means you need the local file system, XFS, probably, for cache. And then you do the long-term storage in an object storage bucket. And in the object storage bucket, you go again to the entire hierarchy of garbage collection that you already know, and you find that in etcd, in Cassandra, in HBase, and in all the other things with the young, medium, and old generation, and all of this collection, and the handling of tombstones, which means that some data, even if in the log, it can no longer be visible, so you can remove it on the read-write. You still have write amplification, you still have read-writes. The log is not the storage, because you need to rewrite it multiple times. But in the end, you have a fast part of the database that is cached on a real file system, and you have a large part of the database that is cached remotely. And that brings us to basically 2014, I think, when the various S3-backed databases at Amazon come into force. And it leaves us with basically today. And we don't know what will happen to databases now or to file systems now, how that will develop any further. Sorry, that took longer than expected.